today we're happy to have DuVernois, Michael DuVernois. I think you said have Mike DuVernois to give the talk. Professor DuVernois received his PhD from University of Chicago in 1996 and did postdoc at Penn State until 2000 and was an assistant professor at Minnesota. And then I think he has his own consultancy and he's all over the world involved in, has been involved in many, many experiments. Well, his PhD background is space-based cosmic ray. That's where he started. And he's now associated with WIPAC, the Wisconsin IceCube Center. And he gave a talk on Hawk. Anyway, an IceCube and Hawk are both water Cherenkov, more or less, so it's very consistent. But I think his biggest distinction is that he has bowled in 7 continents. How did you do it down there? First question.
There used to be a bowling alley in McMurdo.
Oh, okay. Now I get it. Okay, now I get it.
Africa was harder.
Oh, Africa was hard. Okay, so now we have an expert talk on IceCube. So, floor is yours, Mike. Okay, better give you this.
Okay, we'll try this again. Yeah. How's that? Okay. So we're going to talk about some recent results from IceCube, and I'll show a little bit about IceCube construction. I'm a hardware person, so I wanted to show a little bit of that. And Professor Pisa-Chen had asked me to also be giving a talk on Friday, and I'll probably do a little bit more on sort of the logistics and the fun of going to South Pole and building experiments there. Cosmic rays, a figure we've all seen and loved, but in particular want to highlight the connections between cosmic rays and neutrinos are not just the GZK process, but also cosmic ray interactions near their sources. So wherever you're producing cosmic rays, if you're within dense materials, you'll have neutrinos coming, once again, at the same energy scale. So there's this intimate connection between cosmic rays, the material they propagate through, and then neutrinos. If we take the sort of biggest possible picture of neutrinos coming from outer space, we had, and we'll delete some question marks here in a moment, there's sort of the GZK, sort of cosmogenic neutrinos, the possibility of atmospheric neutrinos, want to look for dark matter neutrinos. We know they're atmospheric neutrinos generated by the cosmic ray air showers, and then the supernova and solar neutrinos. Well, where we filled in is just one little place in this map. Again, we're in one question mark. We'll show astrophysical neutrinos in sort of the 100 TeV to a few PeV range. So it's a relatively narrow window that's just been opened by IceCube, but there are real events there. And we really like to see this sort of connection to the gamma rays. It's something that Mr. Camper has referred to as well in OJ. The TeV gamma ray sources extending their spectrum, wanting to count the number of sources. And we'll see sort of a count of neutrino sources late in this talk that sort of agrees with, in a very, very qualitative way, with the ultra-high energy cosmic ray source numbers. So the IceCube collaboration is a large effort of about 500 people, a large number of US institutions, a large number of German institutions, Belgian, and some Swiss, Canada, and sort of scattering of other institutions. It's the collaboration. We actually have, at the moment, 4 people in the 2-meter range. And a very important thing that I learned early on in experimental physics, it takes people of all sizes and shapes to do experimental physics. And I'll represent one of those shapes. Yes, yes indeed. So, so the IceCube experiment lives near the South Pole. This is aerial view South Pole. This is the South Pole telescope. This is a number of microwave background detectors there at the old Maypel lab. The IceCube building, Central Electronics. That's the station. There's the South Pole itself. This is a field of debris. Pretty much everything that's ever been brought down to South Pole is still there. Every once in a while they dig out food from the 1960s. And yeah. Anyway, so IceCube is a cubic kilometer. The footprint on the surface is a square kilometer. These are the locations of the boreholes. The experiment itself resides between 1.5 and 2.5 kilometers below the surface. So we put, I should have switched this around to put Taipei 101 in instead. But the near surface ice is relatively cold, but still has a lot of stratification, and there's a lot of scattering. And as well as bubbles. So at about 700 meters, if you talk to geologists, they'll tell you that the bubbles will all be forced out into hydrates. But they never calculate the time scale for that. So once you get down to about 1,500 meters, the time scale, the tens of thousands of years required, has taken place. And so that's where the detector is positioned. There's also an infill called deep core, sort of a low energy extension, specifically with goals towards dark matter detection and neutrino oscillations. It's a denser, more infilled part of the array, using IceCube as a veto. There's actually a couple hundred more meters of ice below IceCube before you get to the bedrock. And there's one feature through the middle, which is there's a dust layer from a volcanic era that has much higher scattering. So let me sort of show how, in theory, one makes these holes. So the drilling is done using hot water. The first little bit, sort of the packed snow, this is called a fern. It's drilled with this so-called fern drill. Then the deep drill is basically a water nozzle, pumping a couple hundred gallons per minute, most of 1,000 liters per minute, at about 80 C. It's directed strictly by gravity. It just goes down the hole. It's then withdrawn from the hole, leaving a water column. Now, water column is starting to freeze, but there's enough heat that's been put in there so it'll remain large enough to deploy electronics into it for about 2 days. So you have then most of a day or 2 days to deploy the electronics down into it. And we let this play while I talk a little bit about it. I won't explain all the details here, but during the deployment seasons, we ran about 50 people at South Pole. We have 2.5 kilometers of water hose, a series of heaters. The core heaters are actually car wash heaters. In my part of the United States, it can be -30 or -40 during the winter, but you might still want a car wash. So, so that's where the water heating came from. This is the drill being brought up. The tower in which both the drilling and deployment are set up. All of the digital optical modules. So there are nearly 6,000 of these in the ice. It's 10-inch PMT. You can see it one of them being dropped down in, along with digital electronics to digitize the signal, do the timing for the signals, and then do the communications back to the surface. So all done digitally. And then at the central station, software-defined pattern triggers or anything else. Once a year, there's sort of an open period of time when we start a new run. Usually starts in about March or so of the year, where if you wanted to put a new trigger in, you wanted to look for, make up something interesting that somebody would fund you for, and you can write that trigger, calculate how much bandwidth it's going to take up, and that trigger can be implemented. So there are a number of exotic physics triggers for both relativistic and non-relativistic monopoles, cue balls, etc. All triggers like this can just be generated in software, and as long as they're approved, they'll run at the central station up on the surface and collect the relevant data. So it's just the basic setup, the communications and tension cable, and the individual photomultipliers and electronics left in the ice. So the detection principle, a neutrino or any charged particle that comes in, neutrino generates a secondary particle, generates a cascade in this actually very transparent ice. In fact, down at depth, the ice is more transparent than any laboratory material. It's much more transparent than eyeglasses glass, for example. The mean attenuation length is about 100 meters or so in the ice. Anyway, so the Cherenkov light is generated from the cascade, from the shower, and individual photons are detected, and the digitized signals, as well as all the timing information, is then sent to the surface, where triggers are produced. We've got a couple of pieces here. We'll look at two different types of events. So this is the generated photons. Each of these little tracks are generated photons. IceCube was an early adopter of GPU computing. Doing all the photon tracking was much too computing intensive for normal CPUs, but graphic processor units are sort of inherently good at, well, photon propagation. So it's been the way that IceCube has sort of pushed the computing forward. So this is some muon track and the generated photons, and wherever these photons interact with the digital optical module, there's a chance of detection. So a muon type track which has a good pointing information, typically a fraction of a degree up to a degree in some bad geometries. Basically the rows of DOMs are in rows, so there are sort of alleys through the detector which have a little bit worse resolution. The other sort of common topology is a cascade topology. For example, an electron-neutrino interaction, which looks more like a furball in the detector, where you have relatively good calorimetry. You can capture the energy. Here you have energy escaping out the other side of the detector, but you don't have very good angular resolution. And in fact, the typical pointing is on order of 10 or 15 degrees, and that's generated mostly from the timing, from the ability to see that this is not a point source, but has some finite extent. So those are our two basic types of events. Okay. So recording, to just sort of get ourselves orders of magnitude here. Hundreds, thousands, billions, billions. So about 100 billion muons coming in from cosmic ray events from above. About 100,000 neutrino events. Most all of those are from atmospheric neutrinos from cosmic ray showers. And we estimate about 100 astrophysical neutrinos. And so there's a lot of different science being done with IceCube. I'll highlight a couple that I think are interesting, but then I'll focus specifically on our sort of core, the bread and butter neutrino analysis. So the cosmic ray anisotropy, something I talked about a little bit with Hawk, I think is a completely wide open new field in cosmic ray physics. Cosmic rays pointing to things, who knew that? That's not what we learned. So this is from the southern sky. These are downward going in IceCube. And this anisotropy is decidedly changing with energy, and perhaps relatively smoothly changing with energy, but really with very difficult to understand physics. So there's been suggestions that range from heliospheric physics to local magnetic field structures, local matter structures, and I think this is really wide open at this point. Another interesting thing, this actually was never talked about in the proposal stages of IceCube, but IceCube has some degree of oscillation sensitivity on neutrinos, and this particular analysis, this is now old, this was shown last year, has sort of a best fit and 90% contours here. This is for 3.2, 2.3, and it has something approaching the same sort of measuring potential as dedicated experiments that are aimed really at neutrino oscillations. So this is not, I think, exciting in and of itself, just a confirmation of neutrino oscillation, but it shows that you can use a detector like this to make, this is an astrophysics detector, right, orders of magnitude, to make a relatively subtle measurement. And that has really pushed people towards ideas called Pingu, which would be a low energy extension. This would be a detector built within Deep Core, using Deep Core and the IceCube detector as a veto, where one could have the potential to go after the neutrino mass hierarchy using atmospheric neutrinos. Okay. So what I'm going to focus on, though, are the so-called high energy starting events. These are the events everyone has heard of. The sort of 1 per month astrophysical neutrinos, relatively well measured, point on the sky, at our high energy. But I'll also talk a little bit about diffuse analysis and point source analyses. The IceCube experiment is large enough so that these sort of different working groups are at different points in the analysis, 3-year, 2-year, 4 years worth of data, and have different sets of tools being used. Okay, so the high energy starting analysis really came together with first the 2-year analysis in the Science article, and showed some events called Ernie and Bert. And so these initial few, some of these events were actually detected using, as part of the GZK analysis, so analysis looking for very large events, that found a few events near their high energy threshold, and then has been extended to this set of now about 36 events, 1 event per month. It's actually a relatively simple analysis, and the analysis technique is abstracted right here. What we don't want is we don't want muons coming in, so we make a fiducial cut. This region in the middle is that dusty layer, that era of volcanoes that I talked about. We'll ignore that layer because it's a little more scattery, and you might fear that some interaction here could scatter more light in horizontally that you might miss somehow. But what we really want is invisible energy coming in, interaction, and possibly energy leaving. But a very clear separation. So that is, there's an outer layer all the way around on this detector acting as a veto, making a much smaller effective volume. So if we do that, that gives us this, so the 3-year analysis, that's the follow-on to that the science paper, is these 36 events in 3 years, really an event per month, which includes 3 events larger than a PeV. And those first two that were discovered were Ernie and Bert because they had, the person who discovered it had small children. Sort of following that, there's a 2 PeV neutrino event called Big Bird. All the other events have, lesser Muppet character names. We'll leave it at that. If we put the data here, there's a lot going on in this figure, but we'll just indicate the data and then the backgrounds from atmospheric neutrinos, and also there's an unknown component or a not properly measured component of the atmospheric neutrinos via charm production, often called prompt production. So we plot the 90% upper bound on that as well. So these events that we're seeing, these 36 events, some fraction of them are atmospheric neutrinos that have snuck through, for sure. We can't identify them one for one. But a good fraction of them are in excess of the atmospheric backgrounds and in excess of any charm production. So we have to modify this a little bit and say we got some other information. Didn't really talk about this previously. IceCube also includes not just this in-ice portion, but also a set of surface detectors that look very much like OJ tanks, if they were allowed to freeze in, just buried slightly under the snow, which gives us the ability to veto downward going events. So that is, if we know that it's an atmospheric neutrino, we can tell it's an atmospheric neutrino, it's associated with a shower for coming from above. We can't do that for upward going. We don't know anything about air showers occurring half the way around the world, but we do know things about air showers from above us. So if we have, as a function of zenith angle, here we've got the absorption of the Earth. So this is the upward going, coming up from the northern sky. And we have the downward going. By looking for coincidences on the surface, also for looking at multiple tracks, we can significantly cut, both for nu mu and nu e, we can significantly cut into the atmospherics coming down onto us. The prompt contribution remains here. We can't cut it against that. And so one additional distinguishing feature that we gain then is that the astrophysical neutrinos and the atmospherics have different angular patterns, different patterns on the sky. So we have just the energy measurement part, where we're seeing a much larger flux than is predicted. That's sort of one handle. Our second handle is that the pattern on the sky is different between the backgrounds and the sources we want to see. Okay, so for 3 years of data, once again as a function of angle, we show, and this is in actual event numbers, number of events distributed across the sky along with the backgrounds. And so this is for energies above 30 TeV, and I'm going to turn the energy knob. We watch the background fall away from us. Of course, here we're hanging out at 2 and 1 events per bin. So we're definitely statistics limited here. 100, now 150 TeV, and as the events go away, above 300 TeV. The background has now declined significantly. So this set of plots here, that as you go up in energy, your discriminating power increases dramatically, pushes one towards what I'll show only in one slide at the very, very end, how one would think about a Generation 2 IceCube, where to go with an IceCube detector, and that would be to higher energies. Getting away from the edge of the atmospheric neutrinos is a win. Volume out here at a few hundred TeV has a much, much lower background than at a few TeV. So, what can we say about these events? I'm actually not going to show the sky figure, but what I will show, if one assumes an unbroken e to the -2 spectrum, one can get a sort of a best fit normalization. There are no events seen above 2 PeV. There are about 3 expected in this analysis. There's extremely high energy analysis, the GZK analysis, which expects a couple of events as well, which probably disfavors an unbroken spectrum. There's a strong implication that the spectrum of the sources we are looking at here does end somewhere in this range. If instead of fitting the e to the -2, we just want a power law, it turns out around -2.3, and the best fit ends up with essentially no charm contribution. I think there are some other hints that this charm contribution, the prompt contribution, is actually very small as well. And this is just sort of summarizing the spectrum. And so I just wanted to highlight that, that there may be subtleties and details in the middle of the analysis, but the actual events that we're observing are not subtle events. I think I got the scale correctly. These are events that extend over most of the kilometer across of the detector, and most of the vertical kilometer of the detector as well. So these really are the scale of the detector, sort of scale events. And in fact, there was a student project to see how many of those 36 events you could have found if you had just started with, hey, what are the really bright things in the detector? And you find all of them just by finding the set of very large events, and these are a subset of those events. Most of those other very large events are multiple muons coming from above. They're very clearly cosmic ray associated. Okay, let me talk a little bit about the muon neutrino diffuse analysis. So this analysis allows events to enter from outside the detector, so there's no fiducial volume. So this is a statistics increasing analysis, but using the Earth as a filter against muons from the cosmic rays. So this just looks at upward going muons. And this ends up with pretty good pointing, about ½ degree pointing in the sky. And in 2 years of analysis, this group works a little bit slower, there's about 35,000 events. And these are believed to be at least 99.9% pure muon neutrino sample. And actually, most of the residual contribution are taus, which we are not identifying because the 2 interaction points are too close together. Anyway, so this is the just energy spectrum. So once again, sort of